Alright guys, so today we're going to talk about comparing linear and nonlinear functions. So what I want you to do, we're going to have a couple little activities here, but we're just going to go through and we're going to see if we can fill in these tables and then see if we can graph these down here below using each of the triangles. And we're going to use the basis that the side is x and then this side is 2x and use these numbers to substitute in for x. So go ahead and take a second, pause the video, and see if you can do that for me real quick. Alright, so let's work these out. We'll discuss them up here on the board real fast. We don't want to spend a lot of time with it, but it'll be a good introduction to our activity. So, starting up here on the board, we'll go ahead and fill in the perimeter. So remember, perimeter is all the sides added up. So in this case, we have a really small triangle. So if you think about it, we'll start with 1. So here, 2 times 1 would be 2. And then we know that x is equal to 1, so that would just be 1. So what we have is a 2 on this side and 1 on this side as well. So when we add them all up, 2 plus 2 is 4. 1 plus 1 would be 2, so 4 plus 2 would be 6. Next, we do the same thing with the 2. So we take this 2, and we say 2 times 2 is 4, so that means these two sides are 4. And then we know the other two sides are x, so that means 2 and 2. So here we've got 2 plus 4 is going to be 6, and then 2 plus 4 is 6, so then 6 plus 6 would give me 12. Next, I'm going to do the same thing with 3, so 3 times 2 would be 6. So I'm going to have a 6 and a 6 on the sides of lengths. And then the x's would just be 3s, so I have 2 3s. So here 6 plus 3 would be 9, so 2 9s would be 18. Next we would have a 4, so we know 4 times 2 is 8, and then that means 2 sides would be 8, and then on the other side we would have 4 and 4. So here we know 8 plus 4 is going to be 12, so 12 plus 12 would be 24. And then the last one, the 5, we would have 5 times 2 would be 10. So you know that side would be 10, and then the other side would be 5, because x is equal to 5. So we know 10 plus 5 would be 15, 15 plus 15 would be 30. Now, to find the area of those, area would just be multiplying. So here we would say 2 times 1, so 2 times 1 would be 2. Then we would have 4 times 2, that would be 8. 6 times 3, which we know 6 times 3 is 18. Then we would have 4 times 8, which is 32. And then we would have 5 times 10, which would be 50. So that's going to give us all of our numbers in our table. Alright, so if we move down the page, we can then go ahead and graph these to see if it turns out to be linear or non-linear. We should have a straight line if it's true. So we're going to plot the point 1, comma 6. Okay, so that means we're going to go to the right 1, so right 1, and then we're going to go up 6. Now this is 5 going by 5, so 6 would be about right there. And we can be approximate with it. Next we would do 2, 12, so we go to the right 1, 2, and then up 10, 5, 10, and then 12 would be somewhere along here. Next we would have 3, 18, so that's 1, 2, 3, and then we go up 5, 10, 15, 18 would be about it. Next we would have 4, 24, so we go to the right 1, 2, 3, 4, and then we go up 5, 10, 15, 20, 24. And for our last one, we got 5, 30, so that would be 1, 2, 3, 4, 5, and then go up 30. So 5, 10, 15, 20, 25, 30. So based on those dots, you can tell pretty easily that we have a straight line. Alright, so we do have a straight line, therefore the perimeter of these similar rectangles is linear. Let's try this one over here. So on this one, we've got the point 1, comma 2, so we'll go to the right 1 and then 2, so 2 is barely going to be off the ground there. Next we have 2, 8, so we go to the right 2, and then we'll go up 8, so that's going to be right underneath 10. Then we've got 3, 18, so go to the right 3 and then up 18, so that'd be 10, 15, so 18 is going to be in the middle there again. Then for 4, we've got 4, 32, that's going to be way up to 32, so there's 30, so 32 is going to be right above it. And then for 5, 50, we go to the right 5 and then all the way up to 50, which is going to be up here at the top. So when you look at these points, you can see a little bit of a curve occurring. So when that curve occurs, that means that it's not linear. Therefore, areas of a similar rectangle, or similar rectangles, would actually be a curved function. Alright, so go ahead and take a second. It says work with a partner on the next page. It says the table shows the height in feet of the falling object in t seconds. It wants you to graph the data in the table. So it gives you the table. All you need to do is graph it. Decide whether it is linear or non-linear, and then compare the two falling objects and say which one has, or it says which one has an increasing speed. So you've got a falling parachute jumper and you've got a falling bowling ball. So take a second, pause the video, and then we'll work these out after you have it completed. Alright, welcome back. So what we're going to do is we're going to scroll down just a little bit, that way we can get our graphs on the page as well. But what we're going to do is we're going to graph these two and then determine what they are. Okay. So on the first one, we'll start with it. The parachute jumper, it says we have 0 to 300, so we're going to start at 0 and go all the way up to 300. And it looks like here we're going up by 60s. So 300 would be all the way up here at the top. Then we've got 1, 285. So that would be, say if 300's here, then that's going to be 285. We're going up by, that would be 30, 70, 70. So 285 is going to be somewhere along here. Then we're going to have 2 and then 270. So 270 to 270, that means we're going to go up to 40, and then 30 more will be right about there. Then we've got 3 255s, so we'll go to the right 3 and then up 255. So if 240 is right there, then I'm going to go up to 55. I know the next one will be 270, so 255 must be somewhere along there. And then 4 240, so if I go to the right 4 and then up 240, that's going to be perfectly associated right there. So if I look at this line, I can tell real quick, it is a straight line, therefore this is linear. So this one would be linear. Write it out. Linear. Alright, so the bowling ball, that one's interesting. Let's try it. So it says 0 to 300. So we start up here at 0 to 300. And then it says we go from 0 to 300 to 1 to 84. So on 1, we would go up to 284. Now 300 is there, that means 284. That is somewhere along there. And then we've got 236, so we go to the right 2 and then up to 236. That's going to be right underneath here at 240. Then we're going to have 3 and then 156. So the right 3 and then up 156. That's going to be halfway. Let's see, 120s, and then we add 30 to that's 150. So it's going to be right above the line that comes between 120 and 180. And then 444. So we go to the right 4 and then we're going to go up 44. So that would be 30. So 44 is going to come somewhere 30 and 60. So if you look at this one, once again, it's another curved line. So this would not be an example of a linear function. So real quick, just reviewing back over it, we want to switch back here. But if you review back over the questions that we had, it said in the questions that we needed to decide if they're linear or nonlinear. So we know this one is an example of linear. The bowling ball is an example of nonlinear. And it says which one has an increasing speed. Okay, so increasing speed here. We would say the parachute has a constant speed because if you notice, the slope of the line seems to be decreasing at the same rate. But if you notice, the bowling ball is going much faster downward, so that must be the increasing speed. So that would be our example here for our answers. Alright, so go ahead and make sure you have that down. You should have linear on the left side. Bowling ball will be non-linear. Alright, do me a favor and just in your own words, I want you to see if you can answer the question number 3. Once you've got the question answered, you can then move into the lesson. Alright, so welcome back. So we're going to take just a quick second here and we're going to go over a couple definitions and then do example 1. So if you look at here, or look here, it says the graph of a linear function shows a constant rate of change. A nonlinear function, that's important to note here, a nonlinear function does not have a constant rate of change, so this graph is not a line. So we want to associate a line with being straight. So it says, does the table represent linear or nonlinear functions? So we want to pay attention to the constant rate of change here. In other words, we want them to change the same way. So up here on the top, we've got a change of 3 to 6, 6 to 9, and 9 to 12. And each of those is increasing by a number of 3. Down bottom, we have 40 to 32, 32 to 24, and 24 to 16. Here they are all subtracting by the same number. So when we have the same number being added or subtracted, that's going to represent a linear function. So this would be linear. And we can say the slope would actually be the y values over the x values. And we'll talk more about that later. Here it would be negative 8 over positive 3. And that would be the slope. So it changes by a rate of negative 8 over 3. For b, though, if you look at it, top seems to be pretty good. We've got plus 2, plus 2, plus 2. So 1 to 3 is plus 2, 3 to 5 plus 2, 5 to 7 plus 2. But when you look at the numbers down bottom here, we notice that 9, 22, and 55 are not all the same. So this automatically tells me that when the numbers being added are not the same, or being subtracted are not the same, then that means it is non-linear. And like I said, it'll have a different rate of change, and it won't be constant, so therefore it will be a non-linear function. So make sure you have that written down, and then we'll go to example 2. Alright, so looking at example 2, it says identify a function from a graph. So it says, does the graph represent a linear or non-linear function? And explain. So the first thing we're going to do is we're going to pay attention to this graph. If you notice, you see how it has that little curve. I know I didn't draw anything there, but follow my cursor. You'll see how this has a curve to the line, okay? So when it has a curved line, we know that a line is considered to be not a straight line. And if it's not a straight line, then that's what we identify as non-linear. So here we would have an example of a non-linear function, simply because the explanation would be it's not a straight line. Okay? Now, however, over here you notice that our line goes straight across. So when the line is straight, that means that the graph of a line is truly a line, it's a straight line. So therefore it is a linear function. So to explain that, you would just simply explain it and tell us that it's a straight line, therefore it is a linear function. Alright, take a second, pause the video, and see if you can do the on your own. And it says, does the table or graph represent linear function or non-linear function? And explain. So see if you can do 1, 2, and 3 too fast. Alright, welcome back. So what we're going to do is real quickly work these problems to make sure you got everything down that you need down. So on the first one we have a table. So if you notice our table, it's going to increase by 7 each time, so we're plus 7. So we just need the other side to be the same each time and we'll be good. So we got 25 to 20. 20 to 15, and 15 to 10. So here we're decreasing, so we're subtracting. And if you notice, we go 5, down by 5, down by 5, down by 5. So we're subtracting 5. So if it's subtracting 5 every time, which here it is, and it's adding 7 every time on this side, which it is, then that means this is consistent, therefore it is linear. And that would be your explanation. On the next one, we have 2, 4, 6, 8. So once again, we're adding 2, adding 2, adding 2. And this is doing the same thing every time. When we look at 8, 4, 0, negative 4, we're actually doing the same thing there as well. We're just subtracting 4. So 8 minus 4 would be 4. 4 minus 4 would be 0. And then 0 minus 4 would be negative 4. So here, once again, it's consistent on both sides, therefore it is also linear. And it's a constant rate of change. On the next one, however, you notice that we have a line going up, and then we have a line going down. Now, these are 2 straight lines, but because of that changing point, this is not what we would call a straight line. So if it's not a straight line, then this would be an example of a non-linear. So hopefully you got those correct. Pretty easy problems there. If you didn't get those correct, like I said, just go back and review examples 1 and 2, and you should be good. Alright, so the last problem we're going to talk about is example 3. I'll let you try example 4 and then see what the answer is, and then try the problems down below. But what we're going to do on this one is just look at equations. So it says, which equation represents a nonlinear function? So a linear function, a linear equation, is going to be whenever, and you can write this definition down, it's going to be whenever x is to a power 1. Anything that's not to a power of 1 is nonlinear. So to determine the nonlinear function, first I've got this one. Now, I know this one doesn't have an x in it, and it's kind of outside the rule here. So anytime I have y equals a number, or x equals a number, that's also going to fall under as linear. So here, this would be an example of linear. Next, you notice I have this x, and notice how the x is to a power of 1. So that would be an example of linear. Down here in D, I've got y equals x to a power of 1, 4 times x minus 1. So that x to a power of 1, that's to the power of 1, so D is also linear. But when you look at this one's a little weird. You have an x to a power of 1 on bottom. But if we were to write this correctly, we would have to flip the exponent, changing it to a negative exponent, and that would be x to the negative 1 exponent. And the thing is, it has to be to a power of 1, and that negative 1 messes us up here. So this would actually be the correct answer for the nonlinear function. So just keep in mind that when you're dealing with nonlinear and linear equations, it has to be to a power of 1 to work. Alright, so on your own. So number 4, you're going to notice it's to a power of 1, therefore it's linear. Number 5 is to a power of 1, so it's also linear. But number 6 is to a power of 2, so that's nonlinear. All right, go to work, guys.